Alright, hopefully you guys made it through the Pong-Like game with no problems whatsoever. If you're watching this video, you're going to see how we're going to put it together. We're going to try to keep things as simple as possible. Before we get into Visual Studio, let's spend just a minute and talk about a simple implementation plan, because you should always start out with something like that. For us, what we're going to do is have several classes. What kind of classes are we going to have? We are going to have an actor class. We are going to have a player class. We're going to have a ball class. And we're going to have an input class. The player class, or excuse me, the actor class will be the base class for the player and for the ball. So we will be inheriting from actor with player and ball. Okay? Now, the basics. Of course, we're going to need a sprite font. We're going to need a sprite batch because we got to, do all the drawing out to the screen. We're also going to have a few constants to make changing certain elements very easy. So let's take a look at our constants real quick. What kind of constants are we going to have? We're going to have a screen width and height. I won't write those down. Those are obvious. We'll set the screen width to 640 and the screen height to 480. We're going to have a start speed. Start speed is going to represent the speed of the ball when it's first launched. We're going to have our paddle speed. Paddle speed will allow us to easily change that speed in which the paddle moves. Remember, we said it's a constant speed. It's moving up or it's moving down, but it's moving at a constant rate, or it's stopped. So we can set the speed of it right here in the constants. We're going to have a paddle offset. I wonder if anybody thought of doing something like that.
Because you'll notice in the drawing from the simple layout that the paddles were not completely stuck to the edges of the screen.
That's
They're
right.
actually offset a little bit.
All right, let's see. We're going to have a spin percent, so that we can control what kind of percentage that we're going to impart into the ball. And how about text padding?
As well, the text as well was based off the edges of the screen. So we'll control that with a constant so that all parameters for the games, both speed and alignment, can be handled from the very beginning of the game class. We don't have to worry about digging around to change things.
Exactly. And then, of course, not a constant, but we will also have a forecolor, so that we can easily go in there and change the color of everything. All right, so what's the plan after we get all these constants and the basics, the sprite batch, sprite font, etc., all set up? Well, from there, what we'll do is we'll create all of our classes. And once we've created our classes, the next thing we're going to do is we're going to skeleton everything in. So when we start skeletoning in, first thing we're going to do is we're going to start with actor. What kind of things will actor need to store? Well, it's going to need things like a position. Since both the player and the ball inherit from actor, obviously, paddles, ball, they need a position on the screen. Texture. Once again, both paddles and ball need a texture. Screen bounds. We need for our actor to be aware of the size of the screen for calculations that it's going to need to do. Now, let's see, we're also going to need a couple of different methods. How about a move method, so that we can say how far to move an actor? But here's the interesting thing. How about we make this one virtual, so that we can then override it in both player and ball and enhance the movement just a bit. Sounds like a good idea to me. See, what else can we add in there? How about we do draw? So basically, if we pass the reference to sprite batch over to the actor, to its draw method, then the actor can just handle drawing itself. Sounds like a good idea to me. Let's see, what else can we put in there? How about check collision? Because we are dealing with collisions with both our player and our ball. Okay? Very good. So from here, of course, we're going to be inheriting we'll have player. Player is going to need a field for score, so that each player can keep its own score. And then, of course, we're going to override move, so that we can call upon the actor's move to do its bit, basically update position. Then we can do some of our own stuff, because when dealing with the paddles, the player, and we're moving our paddles up and down, we don't want to be able to move above or below the screen. So we can make sure that doesn't happen. Okay, let's see what else. That's good enough. How about ball? What kind of things are we going to find inside of ball? Well, a few different things. We're actually going to set up an enum in here for a launch direction. So that we can specify when we launch a ball, are we going to launch it left, right, or let it be random. We'll set up, of course, velocity and random, because the ball is actually moving, so we need this velocity. And a random, so we can hold a random value. We'll use the constructor for setting up random, so we'll have a constructor in here. I won't jot that down, but at some point, obviously, we're going to need to create the random. Let's see, what else are we going to have? We're going to have a helper method in here that is going to be called range. And the idea is to basically pass in a min and a max. Of course, this is just kind of pseudocode once again. And it's going to return back a float. So just a helper method. We just want to say, look, give us a random value between this and that, and it gives it back to us. Let's see, what else are we going to throw in there? How about we do another override for move. So once again, we will enhance move just a little bit. Let's see what else. How about check wall collision? Let's go ahead and give myself a little bit more room. So that we can see if the ball, has collided with the top or the bottom wall. And launch. How about we throw launch in here, so we can tell the ball to launch itself, and we can give it a launch direction and a speed. And that will get the ball going into motion. Sounds pretty good to me. So there is a quick overview of the infrastructure for each of these classes, fields, and of course methods. Now, we're not going to set up any properties. We're just going to leave everything public. Like I said, organize everything by classes, but let's keep this as simple as possible just to make this a very quick exercise of creating our first game inside of XNA. Starting in precision, we're going to start locking down, getting a little bit more serious about everything. Okay, so with that in place, then what are we going to do? Well, of course, we're going to get input skeletoned in as well. Almost left input out. And with input, basically, we'll just set it up so that we have our single method for taking care of both our gamepad or controller and our keyboard input. Now, how are we going to put everything together? What's the kind of an overview? Here's what I'm thinking, Logan. See if this works for you. How about we start out by just making the paddles display? So display paddles. They don't move or anything like that. We just start them off at a vector of 0, 0. So upper left-hand corner. Then from there, how about we center them? So we can center the paddles. Of course, that means we may want to go ahead and throw in some helper methods for doing that as well.
Right, and also when we get onto those, we'll have to start implementing some of those skeleton methods in the classes.
For sure, and that's really what I'm talking about right here. This is the full implementation.
These are the overall goals, and we'll accomplish them by a combination of implementing the skeleton methods and then using those back in the main game class.
Exactly. So back over here in Actor, thinking about it, this would be a really good place to come in here and put in some, once again, helper methods for things like center X, we can do center Y, and we can do like center XY. That way we can easily center any actor that we want to. So that's a good idea. Okay, so after we display the paddles up at 0, 0, then we center the paddles on the two sides. Let's go ahead and at that point focus on moving. So we want to be able to move the paddles. First, move them by the thumbsticks, and then move them by keyboard. So at that point, you and I both should be able to move the paddles around. Once we've got them moving, then let's go ahead and shift gears to the ball. Let's just get the ball launching. So the ball launches in a random direction, either left or right. Okay, after we get that in place, then let's see if we can make it a little bit more interesting. Let's bring wall collisions in. So we'll make sure that the ball then starts bouncing off the walls. Next thing we'll do, how about paddle collisions? So we'll start checking for collisions between the ball and the paddle. And then we'll wrap it all up by getting a score and relaunching the ball in place. I think that covers everything we were looking for. Does that look good to you as kind of an implementation plan to follow?
Right, if we get through each of those steps, we should have the same result as we demonstrated earlier.
All right, fantastic. All right, so with that, let's go ahead and jump on over to Microsoft Visual Studio Express and begin.
All right, well, this will begin, of course, with a new project. I'm going to name this project knr8.pong. Since it's a knowledge review and we're making a Pong-like game. So we'll create our project. Now, of course, we're going to need some graphical assets because we had the ball graphic and the paddle graphic. So I'm going to do pretty much the same thing we had done in earlier lessons, and that is make a textures folder. And this is where I'll store the actual texture files. I have those files located, of course, in our working directory. So I'm going to copy those out now and move them over to the project directory. So there's our knr8pong, and inside of that is our textures folder, so that we can add them to the project. So we'll add in those as existing items under textures, under content pipeline files, and there we go. Now we're also going to need another asset, and that is the file for the sprite font, so that we can draw the scores. And since that, I already have a font in mind for that, I'm just going to add it as a new item. We'll add in a sprite font. I'll stick with Tahoma, because I have some size and parameters in mind for it. So with this Tahoma font, the size I'm looking for is to be a 16-point size and to be a style of bold for the font. And with that, I'm done with the font file. We'll let the content pipeline worry about it from here on out. And that takes care of assets. Those are all the asset files that we need for the project. The next things we need to look at are things like the classes and the parameters and those constants that we were looking at. The constants we use to control the parameters.
Let's start with the basics. How about we go ahead and put a sprite batch into place? Go ahead and put a sprite font into place. Get those all initialized, set up.
Just get the foundation put in class inside of the game so that things are ready to draw for this type of game.
The begin and the end. Yeah, sounds like a good idea.
All right, so we're going to put in a sprite batch because that's what we'll be using for drawing. And I'll call the field itself just sprite batch. And I'm also going to use a sprite font for drawing the text. So I'll make a sprite font field as well. And I'll just call this font. Now with these, in order to make them usable, we need to remember to create the sprite batch and to load the font.
Let's just do it. Yeah.
So let's get some of these setup things out of the way, beginning with creating the sprite batch inside of initialize. So we'll set the sprite batch equal to a new instance of sprite batch, and of course we need to feed it the graphics device when creating the sprite batch.
Okay.
So that has a new sprite batch instance created for us. Next, I want to load in the font asset into that font field. So I'll jump down to load graphics content and set the font equal to content.load, give it a type of sprite font, and then give it the asset name textures Tahoma, and that will load in our font graphic. Now, one last thing we could do in this base setup is just lay in our sprite batch begin and end, just so we can worry about actual drawing calls once we get around to it. So I want to put in a called sprite batch.begin, and then maybe a blank line and a call to spritebatch.end. And then we're ready to begin using the sprite batch. And while I'm inside of draw, the example game we had set up was to be drawn on a background color of black. So I'll change the background color here as well, just because the colors we have chosen for the graphics will work better on a black background.
Okay. Now we can build real quick, make sure everything's nice and happy. And we're good. Okay, so now let's go ahead and move on to the constants.
All right, let's get the constants in place so we have all of our game parameters locked down. Beginning with screen width and screen height. These are going to be constants, and they'll be both of type integer. The first will be screen width, which I will set to 640, as we had given a resolution of 640 by 480 for this game. And the second will be a constant integer screen height, and we'll set that to 480. Now, in order for these to be meaningful, we need to remember to turn around and actually set our preferred back buffer specifications to these sizes. So
let's do it, yeah.
What I'll do is I'll jump in to the constructor right after we create the graphics device manager. Then we'll turn around and use that graphics device manager to set our preferred back buffer width to the screen width and our preferred back buffer height to the screen height. Now, the reason I'm setting these inside of the constructor is in this constructor, we haven't actually, or the graphics device manager has not actually created the graphics device yet. We saw that when we did a reflector analysis of the game class. And by setting these here, I don't have to do a graphics.apply changes because the graphics device doesn't even exist yet. It'll simply take these parameters and apply them when it is created. But that has our resolution set up and used with the graphics device. Now we can focus on all of the gameplay parameters. So these will involve things beginning with the constant float for our start speed, the starting speed of the ball. So we'll have a start speed, and I've chosen a value of 3f for the start speed. Next we'll have another constant float. This one will be paddle speed. And I'll set that to 5. So I'll have a speed of 5 for the paddle movement. Next will be a constant float for the paddle offset. And this is just the visual offset of how far the paddle is spaced off the edges of the screen. And this will be 10. Next is another constant float. This one will be spin percent. And okay, spin percent will be set to a value of 0.5. So that means whenever the ball comes into contact with the paddle, if the paddle happens to be moving, it'll pick up half of the paddle's overall speed, and that'll be imparted into the ball. And finally, we have our last constant float for our text padding. How far the HUD text, or excuse me, the HUD score is drawn from the edges of the screen. So we'll call this text padding, and we'll set this to 25. There's 25 float, and the reason for this is to move it far enough out of the way so that it doesn't interfere with the paddle.
Right.
All right. Now,
we can go ahead and put our color in as well.
Yeah, because the reason for the color here is that the graphics I'm using are similar to the ones in the input lesson, and that is the graphic color themselves are white. And we're going to use a modulating color to actually color them. So I want to store that color ahead of time for use. So we're going to have a color field as well in the game. I'm only going to use the 4 color since nothing here is technically going to be shaded or filled. So I'm just going to give that foreground green color, which we can give as a new color with red set to 166, blue set to 206, and
57.
57, so red. So green 206, blue 57, and we should be good.
All right, so let's see at this point. Next thing we want to do is now we've got all of our basics set up, all of our constants set up. We've got our 4 color set up.
Let me build just to make sure there's no errors. All right, we're good.
Looking good. All right, so now back to our implementation plan. Next thing we had was let's get the paddles displaying just a 0, 0.
All right.
So let's go ahead and start getting that into play.
And before we start working on paddles, that means we're going to have to take a look at classes.
That's right.
So at this point, it would
yeah, that's a good idea. Let's go ahead and get all the classes set up.
We'll need a class for the paddles before we can create them. So now we have to turn our attention to creating all of the classes and then skeletoning in the methods. And I'm going to begin by adding a folder so that I can organize all of the classes, or all the custom classes anyway, into our own folder. So I'll make a classes folder, and now to that, let me just add all of the class files to begin with. Let's add an actor class, so actor.cs. Let's add a player.cs file. Let's add a ball class. And finally, let's add an input class. So there are 4 classes, as we had outlined in the implementation plan.
Now let's clean these classes up real quick.
Right, because we want to make sure we take off this classes sub namespace, and also make sure that some of the classes, like ball and player, inherit from actor. So let's begin by cleaning some of these up.
And we can go ahead and get the usings in as well.
Right, since some of these classes are going to be using XNA types and not using collections or text, let me take these lines out and replace them with the relevant XNA namespaces. So in actor, the ones that I'm going to add will be Microsoft.xna.framework, so I can get to things like vector2. And also I want to add on the xna.framework.graphics, because actor is going to need to have a texture 2D, and that's found under graphics. And actor, alright, that looks good. Next, let's take a look at the player. And also, I'm going to copy the XNA framework line, because I know I'm going to use some of the types within player. So jumping over to player now, I can replace the using statements. I'll remove the class's subnamespace. And now the player class is going to extend actor. So let me establish that as well. So player extends actor. Next we have the ball. And same thing with the ball. I'll replace the usings with the framework namespace. We'll take off the subnamespace classes. And the ball extends actor as well. Then finally we have the input class, where we'll use a type from the framework, and we'll also use the framework.input namespace, because we're going to be handling input here. And once again, we'll remove the class's subnamespace, and input stands on its own. It doesn't inherit from anything.
Okay.
So it doesn't hurt to do a quick build, make sure nothing simple was amiss, and
everything looks good.
So that's the base classes. Now we can take a look, before we go any further.
Skeleton and everything.
Right, let's skeleton all of the fields and get methods in place.
Okay.
And we'll begin at actor. Actor is going to have 3 fields. It's going to have a position, a texture, and it's also going to hold the static screen bounds value that will be used so that all actors have access to the screen dimensions, and that's what allows them to properly align themselves. So we're going to put in public vector2 for position, a public texture 2D for texture, and let me get the casing on that, and a public static vector2 for screen bounds. I chose a vector2 simply because it's a data type that has 2 components, and that's what I need for storing a width and a height, even though we'll be accessing them through the component names x and y. Also, I'm making these fields public instead of making a private field and then a public member, just because this is such a simple game, and it does alleviate some of the headache of messing around, like, let's say with the component of a vector2 when we're outside of this class. This allows us the ability to set maybe only the x component, instead of having to completely retrieve the entire vector2, change it in a temporary variable, and then restore that entire vector2. But these are the fields that we'll need for actor. So now let's skeleton in the methods that actor is going to contain. This will begin with the public virtual method move. So we've got public virtual. We're not going to return anything, so we'll have a void return type, and the name will be move. Now we want to take in a parameter, a vector2, for the movement amount. And this is simply how much to move when we make this call. And next we'll have the draw method. This will again be a public method, no return, and we'll call this draw. Draw is going to need to take in 2 things. It's going to need to take in a sprite batch to perform the actual drawing, and we're also going to take in a color, since here in the actor class we have no idea what color the game is going to be running under. That's handled under the game class. So instead we'll take in a simple color parameter so that any actor could be drawn with any color. So we want our sprite batch parameter to be called sprite batch. and our color parameter to be called color. Alright, next method will be the center X method, one of the helper methods you were talking about. So this will be public, no return, and center X for the name, no parameters. And we're also going to have a center Y method. So same as center X, center Y. And then we'll have a third helper method, and that is to center on both X and Y at the same time. So this will be a public void center XY. And even though we're just skeletoning in methods, since the only thing that center XY is going to do is call both center X and then center Y, we have everything available here. Everything's defined at this point. So I could just throw in the implementation for this one. That is a call to center X, followed by a call to this dot center Y. We'll get that out of the way just because that's apparent. We can implement that because we already have the methods defined.
Sounds good.
Alright, now two more methods we need to have inside of the actor class. We need to have a check collision method, and this one's going to be interesting because what this method check collision is for checking the collision between two rectangular actors. All actors by definition, since we have a position and then a texture width, they're all going to be represented on screen as a rectangle. Now we need a helper method somewhere in this game that will allow us to take two actors and tell us if they intersect, if they're colliding. And the most logical place that I could find to put this was inside of actor itself, since the method's going to work on actors. Now the key here is that this isn't technically going to be part of any instance of an actor. It's just going to be a general method. So I'm going to define this as static. As a matter of fact, I'm going to define it as a public static method. We'll return a bool to represent whether or not the two actors were colliding, and we'll call the method check collision. Now check collision is going to take in the two actors to test to see if those actors are colliding. So we'll take in two actor parameters, one actor A and the second actor B. And these will be passed in. Some calculation will be done given their width, height, and position, and then a value returned for whether or not they're colliding.
Okay. Now, you said a second ago that there was two more methods.
I might have just been looking past the end of
okay,
of
good
that
deal.
one.
I was trying to figure out what would be the other one you'd need. Okay,
I was
deal.
looking on to another class.
Excellent. Okay, so that's everything in place for actor. Let's go ahead and move on to player. Get that skeleton.
Actually, let me do a quick build because I already see some methods that have a return type that are going to break.
Okay.
More specifically, the check collision. It returns a bool, and I'm not returning anything
just return true for now.
So,
or false.
I'll return false, though I don't intend to use this method until I get around to putting an implementation in. And aside from some warnings, we now have actor and a state where it will build.
Looks good. Let's go ahead and get player skeleton in real quick.
Alright, player should be simple.
Yeah, it is.
All we're going to have is the field to store score, and then a method that is an override to move. So let's drop in the score. This is going to be a public int called score. The method is going to be an override. So public, let's see, override. We're going to be overriding the move method. So I'll drop that in, and for the time being, I'll leave the call to base.move.
Okay.
So that takes care of player.
All right, let's go ahead and move on over to ball.
All right, ball is going to have a few things. One thing beginning before the class itself. We had talked about how the ball needs to launch in a specific direction. Now, on game start, it can be a random direction, left or right. But we had talked about when a player loses, the ball will be relaunched towards the winning player, always towards the winning player. So we need to have a way of specifying direction. And a clear way of doing that would be to put together an enum that has the directions we want to use. So let me define that here as an enum launch direction. And the elements I want inside of that are left, right, or random, are possible values for the launch direction. Alright, now moving into the ball class itself. We need to have two fields, one public field for velocity, and then a private field to hold an instance of a random object. And that random object will be used to generate the actual random values, because we talked about that the ball is given a random angle that it moves at. So we'll need that random object in order to generate those values. But first is the field for the public vector2 for velocity. And then we'll have a private random, and we'll just call that random. Alright, now we have a handful of methods that we need to have skeletoned into the ball class. Let's see. Let's begin with the public constructor. Because we'd briefly mentioned that there was going to be a constructor, and we had said that we needed something to create the instance of the random object. And we're going to do that inside of a public constructor.
As a matter of fact, go ahead and just code that in now.
Right, since that's all internal, no external dependencies on this.
Right.
So let me jump in and create the random object. So random equals a new random, and now that's out of the way.
Okay.
Alright, the first method that we need to skeleton is going to be a small helper method that's designed to give us a random value, but take in a range, so we can specify a minimum and maximum and get some number in between. And I'm going to define this as a private method, since it's only used inside of the ball class. I'm going to return a float value from the method, and I'll call it range. And range is going to take in two parameters, a float min and a float max. Alright, next method. Let's do an override to move, since the ball is going to need some special considerations in what move may have it do. So let me put in a public override to the move method, and I'll leave the call to base.move for now. Next, we're going to have a method that will allow us to do the actual launching, because the next thing we need to worry about, if we're following from the implementation plan, we're saying that one of the first things the ball is going to have to do is to be able to launch in a specific direction. So let's lay in the framework for the launch method. It doesn't need to return anything, and I'm going to call the method launch. Now, launch does need to take in some parameters. We need to be able to specify a direction that we're launching the ball in, and then a float for the speed of the ball after it gets launched. So I'm going to take in a launch direction in the parameter direction, and then a float for the speed. So that should be all the control we need over launching the ball. And finally, there's one last thing the ball needs to be able to do, and it needs to be able to check the top and bottom walls to see if it has hit them. And if it has hit them, it needs to bounce off and begin moving in the other direction. So I'm going to put in a method. I'm going to start this out as a private method because I have a certain way in which I'm going to call it. So we'll do this. This could almost be categorized along with range as a private helper method, since the whole idea is that this happens contained within ball. So I'm going to make a private void check wall collision. And I don't need any parameters to it, since it should have all of the information available to make the check. That includes its own position and then the actor's screen bounds field.
Okay.
And with all of those, let me do a build, make sure I'm not missing a return on any of these methods.
Okay, yeah, the float.
And here we go. Let's temporarily just return 0f, just so that we can build and
make sure everything else is error-free.
And everything else is just warnings.
Cool.
All right. Well, that leaves just the input class. So let's jump over to input, and let's skeleton in the one method that we'll have here. The idea of the input class itself is more for organizational purposes than for functionality. The idea here is that we have a series of things we need to do to process raw input and get a desired output. So what I want to do is put together a static method, since there's no reason to have to create the input class, and we would never need multiple input classes. So I'm going to make the method, and with that in mind, probably the entire class could be static as well, thinking about it, since the only method we're going to hold is a public spelling. So a public static vector2 called get paddle input. And the idea with get paddle input is that this is a general use method, so that we could call it either for player 1 or for player 2 and have it return input off of either that gamepad or that set of keys for the keyboard.
Right.
So in order to indicate which player that I'm looking for input from, I'm going to pass in a player index. And I'll call the parameter just something like player index. So that way we can use the pre-existing player index, which has values like 1, 2, 3, or 4. And we can use that to determine which player we're trying to get input from. And let me put in a temporary return, just so that we can build. So I'll return a vector2.0, just so that we can build and still only warnings, so that has the skeleton in place for each of our classes.
Looks good.
So now we can go back to the implementation plan, which I believe...
The very first thing is getting the paddles to display at 0, 0.
Alright, so we need some paddles. And for that, let me think.
Well, we can start out by going and loading the textures, or do you want to go ahead and set up some of the...
methods?
There's so many different ways we can go here.
Well, we have all of the types defined, so let me start by dropping the... excuse me. Dropping the fields down back in the game class.
Ah, I like it.
So back in game 1, let's jump right below the color, and let's put in, 2 players, or 2 paddles. So these fields will be of type player, and I'm going to call them player 1, spelling.
Almost.
More spelling. Player 1, and another player for player 2.
Spelling.
Alright, more spelling.
Perfect.
Awesome. So we have 2 players.
So let's go ahead and create them now.
So we need to remember to create them before we use them. So to initialize, we'll create them as player 1 equals new instance of player, and player 2 equals a new instance of player as well. And that reminded me of something else. Once we get to, you know what, I'm going to purposely hold off on that. I want to skim over it, and we'll address it as we need to. Because the next thing that we want to do is worry about getting the texture. And then once we have the texture loaded, we can position them. You'll notice I'm being careful not to position them yet, because the positioning, if you think about it, the way we've positioned things, especially centering, is based on a width and a height. We haven't specified that yet. What we're going to do is use the textures dimensions, width and height.
Right.
And we don't have textures loaded yet. We're not going to have textures loaded until we run load graphics content. So I'm going to jump down to load graphics content so we can get those textures loaded into the player instances. So I could begin with player 1, and say that player 1's texture is going to be equal to content.load, and we'll take in a type of texture 2D. Then the asset name will be under textures. We'll have the paddle graphic. So textures paddle, and that should take care of player 1. And then for brevity's sake, let's copy and paste that line so that I can change it and load player 2 as well. So now we have all of the graphics loaded in. And now that we have the graphics, we have, of course, position is going to default to 0. So now we could jump onto a few other things just so that we can see these drawn on screen. And those things are going to be the drawing from Sprite Batch. So let me jump down to Sprite Batch. Now that we have textures loaded, we can take our player 1, tell it to draw, and we'll have it draw using the same Sprite Batch, and give it a color of the value held in 4 color. And then I'll copy paste this line, maybe even space some of this out a little bit, so that we can draw player 2 in the same manner.
Okay.
So now, let me build, and...
should be able to run and see it.
Well, let's try.
And up. What are we missing?
Well, we're missing... we've got calls to draw. We're missing implementations.
Okay.
We've been running thus far off of pure skeleton methods.
That's a fact.
So what does draw do?
Nothing at the moment.
Absolutely nothing. So that would be the first method to fill in. Let's put together an implementation.
See how we can
draw.
let this kind of walk us through what needs to be coded in first?
All right, let's address draw. Draw should be simple, as we have everything that we need to know as far as positioning and textures. So let's do a call to draw. Let's use the second overload so we can use vector positioning, and let's draw using our current texture. So this being an actor has a texture, and we'll feed that to the draw method. This again being an actor has a position, which can be fed in as a vector 2. And then color is going to be supplied by the parameter color. And that will make up our very simple draw
Now
function.
I am for sure it'll draw. And there it is.
Oh, look at that. So we have actual graphics drawn to the screen now. Next, we can move on to positioning. We get the paddles positioned in their initial starting state.
Get them centered up and then get them pushed in off the sides.
Right. And looking at this, now we can look into the future a little bit and see that we need to implement things before we use them. Let me drop in an implementation for center X and center Y so that that can be used when we're trying to center the paddles.
Okay.
Let's begin with center X. Now, centering is, of course, going to affect positioning. So what we're looking for is to set this dot position, and we're centering in X, so this dot position dot X to be equal to some value that is centered on the screen. That means we need to take into account the screen's height. We have the handy screen bounds field, So we can use the screen bounds.
Screen's height or width?
On
X?
Center X, width. Yeah, it should be width. Oh, I was saying the word height, wasn't I?
Yeah.
Okay, yeah, no, not height. I was saying height and typing X.
Yeah.
The two just didn't,
it's like, my head hurts.
No. Center X, and we were dealing with width.
We're just testing you guys.
All right, so we're looking at the screen bounds X, so that should hold the width of our screen.
Mm-hmm.
Now we want to take half of that width to center up on the screen, but then, of course, we need to take into account the actor's own width.
That's
so
right.
let's subtract back from that and get our width, which is held in this .texture.width, and let's divide that by 2.
Yeah, this is something you guys have seen several times.
And since we're going to use it over and over again, it just made sense to drop it into a more convenient method.
So now we can copy and paste that and change X to Y and width to height.
All right, so down to center Y, where we're centering the position.Y. The height of the screen is held in screenbounds.Y. And the texture should be based on the texture's height. And all the other calculations should be the same. And center XY has already been set up. So now it's back to game.
Okay.
Alright, so to put this into action and to center up the players, this does need to be done inside of load graphics content because, again, we're relying on that texture to exist so that we can use its width and height. In a more advanced game, this might be delayed even further until you have something like a start game method.
Mm-hmm.
But since this is so simple and kicks off automatically from the beginning, this is the point we have to get to before we can start centering things.
Right.
So let's focus on player 1. Let's get it centered. So let's take player 1 and tell it to center in...
We'll center in Y, up and down, yeah.
Center in Y, and let's see.
Because we'll need to take that, and then we're going to need to offset it. And then for player 1, all we need to do is offset it, the paddle offset.
So player 1, let's take its position, .x, and let's set that to...
That paddle offset.
Let's see, grab paddle offset.
There it is.
And plug that in.
Now, player 2 is going to be a little bit more interesting. Yeah, we can go ahead and test it right now.
Because I think there's already going to be another problem. That's what I was skipping over earlier. Because, I mean, up to this point, it seems like, well, everything will be happy. We used our screen bounds, and so everything was convenient. Except that we're now... The spacing worked, the padding offset worked, but look at player 1. It's up off the top of the screen. Why is that?
Because we haven't sent over that screen bounds information yet.
Exactly.
We need to go and initialize that.
We have screen bounds, and we've never initialized it.
And so the actor, of course, is thinking that the screen bounds is 0 and 0.
So let me jump into the very beginning of initialize, and let's set that up before anything else gets set. So let's set our actor, let's see, the actor had the static field screen bounds, and let's set that to a new vector2 to represent screen width in X and screen height in Y to hold those for later use.
So now when we divide by 2 and all that good stuff, we know where to set it. And there you go. Very
so
good.
now we have player 1 positioned. And now we move into player 2, which is where we were talking about some of the right-hand side offsets. Alright, so for player 2, well, the first part's easy. We can do the center Y for player 2 as well. So player 2 dot center Y. That has player 2 centered on Y. Now we need to get it to the other side of the screen. So to get it to the other side of the screen, let me put in player 2's position, now dealing with X. And the other side of the screen is screen width. Now, of course, since it's left aligned, since we have an origin of 0, 0 right now, if we actually set it to screen width, it'll be off screen to the right.
Actually, I can show this real quick. If we jump over here and pull up I can use just one more of these sheets real quick. So basically, if we said, here's the top and right side, if we told it to use the height, where's it going to draw? The width. It's going to place it right here because there's our 0, 0.
We put the top left at the full width, so the rest of the image is going to draw to the right of that. And to the right of that, at that point, is off the screen.
And we're looking for it to be over here. So there's 2 more things that we're going to need to take into account.
So we're going to need to subtract some of that overall screen width back off.
Yep, we're going to need to pull his width. That'll put him back to right here. And then to move them over even further, then we're going to need to subtract that padding.
Exactly.
Very cool.
So let's put that into place to get the correct positioning going. So we know we're starting with screen width so that he's stuck to the right-hand side of the screen. Now we also need to subtract out his own width, that is player2.texture.width. So that'll stick him just visibly to the right side of the screen. And then one more offset, and that is the paddle offset. And that'll bring us a full paddle offset back onto the screen. So now we have the paddle positioned as he should be, stuck to the right-hand side of the screen, but pulled in based on that offset.
Excellent. So according to our implementation plan, we've now centered up our 2 paddles. Next thing we were going to do is get some motion.
All right. Well, motion for the paddles is going to come from input, since some form of input has to be given to move the paddles. And that means we need to turn our attention to the input class.
Okay.
So moving over to input, it's now time to start some implementation for getPaddle input. I'll wipe out our temporary return so we can start on some real code.
Okay.
The first thing I'm going to do is let's drop down a direction variable. Let's drop down a vector2, and I can use that to continue to process the input. So we get some raw input, then maybe make some changes to it before we actually return the input.
Okay.
And I guess just a full overview of what I'm looking to get out of this method, and that is, you can see we're returning a vector2. The idea is that I want to return some type of normalized output, so a normalized output vector, so that I can rely on that vector. Basically, this vector will be going up or to be going in Y up, Y down, or to be 0, not moving at all. And we'll use this method to reroute any input we get from the gamepad, any input we get from the keyboard, to get that final desired output.
Okay.
So let's begin with direction. I'm going to drop down the vector2 direction variable, and then immediately turn around and initialize that by the gamepad. We'll get input off of the gamepad first. So in order to do that, and in order to make it fit on the screen better, I'm going to throw down a gamepad state variable. So gamepad state called gamepad state, and we can use that to capture the state of the gamepad. So we'll take gamepad dot getState. GetState is going to be looking for a player index, but we have one of those in the player index parameter. So the use of player index here means that this function works directly with the gamepad very easily. So now we can turn around and I'll initialize the direction variable. So that direction is equal to, instead of directly using the thumbstick, I want to define a new vector2. The reason I want to do that is I have a specific value in mind for the X movement. The paddles never move in X. They move only up and down.
Right. So
I'm going to lock in a value of 0 for X in paddle movement.
Okay.
Next, we're going to need, for Y, I want to use the left thumbstick's value to drive Y. So we can get that from gamepad state dot thumbsticks dot left
dot Y.
Dot Y. And end off that. And that will be the very start for our direction. Now, there may be some other calculations we do in the future, but for now, let's just return it.
Yeah.
Let's return direction, and then we have some value now, driven based on a gamepad.
Okay.
So with this simple implementation, I'm going to build very quickly, make sure we don't have any errors. Now we can turn our direction momentarily back to the game, so that we can see how can we use this in conjunction with the paddles to make them move.
Okay.
And to do that, I'm going to jump down to the update method. So inside of update, what I want to do is I want to get the value of the current input for player 1 and then for player 2. And I'm actually going to store these values in variables because I will need to reuse them later when I go to do the ball spin. I'll need to know how fast the paddle's moving. So we'll remember that with the variable, a vector2. And for player 1, I'm going to call this player 1 velocity. So we have a player 1 velocity. Now velocity is going to be equal to input dot get paddle input. This is player 1, so we'll feed it a player index of 1. And now, like I talked about, the goal with the get paddle input is return a vector with a length of 1. But our speed is different than 1, so what I can do is apply speed after I've gotten this input value. So we can take our input value and then multiply that by paddle speed, so we get the actual desired parameter, speed.
Okay.
Once we have this saved into player 1 velocity, the first thing we can do with that is to move the player by that velocity. And that means taking player 1, telling it to move, and then giving it player 1 velocity for the movement amount.
And we haven't yet implemented player's move, but we do have the inherited move calling being
base.
Called. So yeah, we're good.
That is a good thing to point out, though, since in Actor we don't have any code for move, so move doesn't do anything yet. It wouldn't be a bad idea to plug this in.
No, we can go ahead and do that. We can get to player in a few minutes. I want to show them a couple issues that pop up.
Yeah, let's put in this
so we can just affect the position by the amount.
Plus equals amount. So move the position by the amount. and that is the base code for move. And since this is inherited into player, we don't
actually, going over to player, and you can see player's already calling its base, so everything's going to be good there.
All right. And now I think at least for player 1, we should be able to build and test.
And I can grab a controller, and here we are. And as I push up, I go down. So as we've talked about in the past, we've got this inverted Y, okay? Because, of course, as the graphics go down on the screen, that's Y getting larger and larger. It's incrementing. And as I push up on the thumbstick, that's an incrementing number. It's a positive number. So we need to invert that. So this is inverted. And, of course, look at this. I can go off the screen. And also, look at this. I can push up just a little bit. And I'm controlling this with the analog input right now. So I can go from slow to fast. So that's another thing that we need to take into account. But the good news is left and right doesn't work.
All right, so we at least have that locked down.
Yes, so that one's working right.
All right, let's start to address some of these. Let's begin with the inverted thumbstick.
Okay.
Let's go back over to the input class. And since the thumbstick's value for X and Y is opposite the screen space for Y, I can simply invert this. So we'll say minus gamepad thumbsticks left. And now if you move the thumbstick, there we go.
So that part's right.
All right, next thing we need to address, as you had pointed out, that the input is not behaving in a digital fashion. It's taking the analog input and allowing an analog speed difference, variable speed. So let's put together some code to let us normalize the speed. So we either have fully on or fully off.
Okay.
So what I want to do, in order to get rid of the lesser movements, is to normalize the vector. Now this seems simple enough to do with a vector 2. Since direction is a vector 2, we can tell it to normalize. And again, normalizing just meaning reproportion the values so that the overall length of the vector is 1.
But Logan, that's not a number.
Well,
this is actually funny. Let's prove it.
Let's see what you mean, though, because, I mean, it seems like this would work. If we took maybe, let's say we were moving the thumbstick half up, that would be 0.5. The real desire is to have a full value of 1, so that multiplies properly by the speed.
Right.
So the idea is that this should work. What we see is nothing.
Oh, where'd the controller go?
The paddle has disappeared entirely. And that can be an unexpected result at first. So I'm going to take just a minute and let me step through this and see what's happening with normalize. I'm going to set a breakpoint on normalize and rerun the game. So our breakpoint hits at normalize. And what is direction right now? It's a value of 0, 0. The thumbstick hasn't been pressed in any direction yet. So if we try to normalize a value of 0 by 0, if I step over, it's now holding the values not a number and not a number. Okay, well, how is this going to affect our speed? I'm going to step over again so that we step back into the game. Now the player input velocity, if we step over this line, is now not a number because we multiplied not a number against paddle speed. So our entire velocity is not a number.
Didn't cause anything to explode. It's just not a number.
Now we're about to move. And if we move by not a number, let me step into, I'll step into this one. So if we move, I don't have position available. I see what I was going to do. Let me step back a little bit. So if we move and then look at player, after we have moved by not a number, there's our position. Our position is now not a number. And so at this point we can determine by looking at the result, if we try to draw at not a number, we simply don't draw on the screen.
Love it.
So that's where our problem's coming in. So we need to make sure that we never attempt to normalize a value of 0 by 0. So that means I'm going to need to put in a check to make sure that we don't do this. So I'm going to put in a check to make sure that our direction, let's take the length of that overall vector, make sure that we have some value. So if the overall calculated length is greater than 0, for greater than 0, then we have some values. If we normalize those values, we'll get an actual normalized unit vector and not a number. So with this now, if I build and run,
woo!
Now
Let me try to go slow. Oh, I can't go slow. It's one constant speed. And trying, nope, just can't do it.
So we could call it there for the normalization, but I did want to point out a few things. This is, of course, normalizing in any case where the direction has any amount of value put in. So that means right now we're relying on the default dead zone of the controller to work accurately. That would mean that, let's say we had a faulty controller, and for some reason the thumbstick gave values that were high enough to cause there to be some length. What that would mean is that we would have no control over the joystick moving on its own if the joystick was off a little bit. So if we wanted to set that up, it seems easy enough because what we're doing for the check is greater than 0. That means it would seem like we could put in a value of our own, like maybe even all the way up to 0.5, so we'd have to put a significant amount of motion into the thumbstick. The problem with this is we've just broken our digital input setting. because what this means is now we could escape if we had values of maybe 0.1 or 0.2. We could skip the normalize and retain our 0.1 or 0.2 and hand that on, which means we would retain some analog movement.
And you can actually see that if you run it real quick. So there I moving, but watch this. Less than 0.5 still has that analog control.
Right. So if we wanted to put in custom dead zone limiting, we would need to code in an else to make sure that if we had detected that we don't want to move, really make sure that we don't move by setting the direction to be equal to 0. I'll zero that out by just hitting it with vector 2.0.
And so now if he runs it, you'll see that just a slight push up, I'm slightly pushing up. I'm actually almost at 0.5 and it's not moving, and I'm at 0.5. And I got that one constant speed. So right now, again, I'm just slightly moving up and down, no motion at all.
So we can both account for a bad dead zone, or we could even adjust how much you're supposed to move the thumbstick before it'll react. So far, though, the value 0 has been fine. Both of our controllers work fine with the default dead zone calculation. So I'm going to leave it 0, but I'm going to leave the rest of this code in because it is useful if we ever decide to change the dead zone for the controller.
Okay.
And all right, I think that's everything we needed for the gamepad input.
It is. Now let's go ahead and move our attention over to getting a keyboard since we're focusing on getting these paddles running.
I just thought of something. Maybe before we do that, let's get the other player in.
Okay.
Because we've worked with this player index, but haven't proven that it'll work for 2 players. So let me jump back to game for just a moment. And the whole idea with creating this input class was to make the input simple for duplicating over to another player. So I should be able to simply grab these lines, make a different variable for player 2 velocity, and then get the paddle input for player index dot 2, and apply that movement to player 2. We're applying the player 2 velocity. So now I can use my controller and move player 2. So there, the input class is working very well for us, as we can implement 2-player movement very easily now.
Looks good.
So with 2-player movement, that leaves one thing for input before input is finished, and that is keyboard input.
Okay.
So let's take a look at doing that. What I'm going to do for the keyboard input is I'm going to jump in between the initialization of the direction and the normalizing code, because I'm actually going to leverage the normalizing code in order to handle and combine the keyboard input. But for the keyboard input itself, let me do the keyboard state, and then I'll address the problem with the 2 players. So let me make a keyboard state variable so that I can, set up keyboard state, and then pull the state of the keyboard with keyboard.getState. Then we can do a turnaround and look at and do some checks to see if the up key was pressed, move up. If the down key was pressed, move down. So let's say if, I managed to mess that up, if keyboard state dot is key down, let's feed it. I'm going to use the arrow keys to begin with. Then we'll need some setting later for 2-player. Let's start with keys dot up for moving up. So if the up key is pressed, then we want to take our direction and move up on the screen, which is -y. So I'm going to take the direction vector we've got going on, take its y, and decrement that by 1. And then I'll copy this if statement. So we duplicate that down, and now I can look at the down arrow key. And if we're moving down the screen, I can increment y by 1.
Okay. But this is going to cause an interesting problem because right now we're not paying attention to, is it player 1 or is it player 2? So you should see both players move.
Oh, let's test it. So moving the up arrow key and the down arrow key. So both players are moving.
Let me grab my controller.
Time.
I can fight you.
So we can keep an offset going, but the problem is we're not differentiating between keyboard input for the players. We're grabbing player 1, moving with the keyboard, player 2, and also moving with the keyboard.
Right. Making the game less fun.
Though things that are working for us is I can take a look at moving the keys. Because I set up the direction, let me move this window out of the way. We have the direction being decremented or incremented. That means if I press up and down at the same time, we simply stop. So we don't have to worry about one key overriding the other.
Cool.
We're decrementing but then re-adding that value of 1. Also, since we're not overriding that value, I can take the controller now. So using the gamepad to move this paddle, I can move it up, but then press the down arrow key and fight it. Or move it down and then press the up arrow key and fight it. So that properly combines everything. The reason we're getting this effect and not moving it too fast, because, for example, if I move the gamepad up and then the key up or down, it doesn't allow me to move faster. The reason for this is because we had put in normalized code to handle digital input on the analog thumbstick. This also works in our favor if we come up with a vector of more than 1.
Right.
it will still get normalized back down to a unit vector of 1. So with this in place, that allowed us to get away with simple keyboard input. But the one thing we have to address now is the fact that we don't have true two-player control. We need to differentiate between the players to assign a different set of keys. So let me set that up. Let me actually make two variables, an up key and a down key, so that I can assign those to one set or another. So I'm going to make a few keys variables. First key I'm going to call up key, and second key will be down key. Then I can turn around and do a check and see which player we happen to be looking at. We could start up an if statement, and we could say if the past player index is equal to player index.1, well, then we're looking at player 1. If we're looking at player 1, player 1's keys were W and S. So let's put in up key as keys.W and down key as keys. Whoops. And
Don't worry, guys. I called the other one too.
So keys.S, and it's a little bit of spelling, and then we're good.
Perfect.
Now I'm going to copy this block, because otherwise, if it wasn't player 1, it's going to be player 2. We're not going to factor in for more players since Pong is only going to be 2-player.
Right.
So I'll handle the rest of this with an else. And in the else case, I want to set the up and down keys to the arrow keys up and down. So that is keys.up or keys.down. And now with these key variables, let me plug those in down in our keyboard is key down checks. So that we check
is key down takes a keys type, so works out perfect.
So we can check the up key or the down key. And that way, now if we build and test, I can move the arrow keys and move
reach over here and hit W.
So now we have independent player movement based on the keyboard, and we still retain gamepad movement.
Beautiful.
So that's really it. That has input working exactly the way we need it to now.
Beautiful. Okay, so let's see. Implementation plan. What do we call for next? The very next thing that we were looking for was getting the ball to launch.
All right. Well, ball movement, let's shift our focus over to the ball class. Now, in order to get the ball to move or to launch for the first time means we will need the launch method. We'll need an implementation for that. And we'll also need its helper method range. I'll hold off on range for just a second until we see what it is we need out of range.
Do you want to do the same thing that we did with our paddles? Go ahead and jump back over to game and go ahead and define the ball and get that set up with the texture?
Yeah, that'd be good. Let's get the simple stuff in place first. Let me go back to the game, right below where we declared the player fields, and declare a ball field. Let's call it ball. Then, like we did with the players, we should create it and initialize. So ball equals a new ball. Then we need to turn around and load its texture. So I'm just going to copy the line for player 2, paste it in, and we'll say ball dot texture equals the texture's ball asset. And then we shouldn't worry about any positioning because we're going to launch it. Though we could do something like a call to ball.launch since the launch method is defined. The idea here is that we launch the ball, and now we need to launch it in a direction. Well, we've got that enum defined, so we can give it a launch direction of random. The game has just started, so we're not going to pick a player to launch the ball at yet. We'll just launch it randomly. And the speed we have defined as a parameter for the game in start speed. So now we have our call in place, and now it's time to get that implementation down. Okay. Unless you want to put in the code for drawing.
We can go ahead and call on draw, too. No reason. Just right after player 2, just put ball.draw.
So we can go into player. We might even be able to run, because even though launch isn't going to do anything, we'll at least see it on screen. So let's draw. We'll give it the sprite batch and give it the foreground color. For color. So now we can build, run. And there in the top left-hand corner of the screen, the ball is, in fact, drawing.
Okay.
Now we just need to worry about getting some motion working. And the motion, granted, the motion is going to be in two parts.
Yep.
Launch starts the motion, but we still need to apply it. The motion I'm talking about is its velocity. If we look at ball, we have a velocity field. That velocity controls how fast it moves, but nothing actually moves it. Nothing actually calls move. And right now in our game, for the players, we're calling move from with an update. So I could put that in just so we have the background code in place.
I agree.
We could do something like a call to ball.move, and we can move ball along by its velocity. So we'll plug in ball.velocity.
Okay.
so that once we establish a velocity, we'll automatically have the ball moving.
Sounds good.
Alright, now back to ball. I think now we can focus the rest of our attention on launch. Alright, first thing that launch needs to do is center the ball on the screen, since it always launches from the center of the screen. So before we worry about any other calculations, let's put the ball this dot center, and we'll center on X and Y. Okay. So we'll call the center XY. We could even test that, and there we
Perfect.
go. Ball centers on X and Y. Now we need to talk about how to move the ball in a desired direction, because there's a few approaches we could take. We could do something as simple as assigning a random value to X and Y.
Mm-hmm.
But that would be hard to control, and it would be very hard to get a desired speed. And this method is designed so that we specify an exact speed. So we need to come up with some method of giving a direction to the ball that takes into account an exact speed. So the idea here is we really need to separate the idea of direction and speed. And to do that, the way I want to represent the direction is by using a rotational value. I actually want to specify a rotational value in radians, so a percentage around a circle, and use that for the angle to launch the ball. So let's start with this value, and then I'll implement the calculation, and then we can start taking a look at exactly which directions we're getting out of this. The way this is going to work is I'm going to define a variable. I'm going to call that variable rotation. And then in rotation, I'm going to store the value math.pi. Well, let me begin with 0. I'll get to that in a second and explain why I need that. Let's store a value of 0 in rotation. And now the calculation to turn this value in radians, into a velocity x and y is going to require the use of sine and cosine to apply it to x and y. So what I'm going to do now is apply the rotation to the velocities x by using math.sine for the rotational value. So we'll plug in rotation. Now math.sine is going to be a double, so I'll need to cast this to a float in order to store it. And then I can copy the line so that I can store the y value. And y is going to be based off of the cosine of that rotational value. And then finally, once we have rotation x and y,
we can just basically multiply it by speed.
Since there should be a value of 1. Even with this, though, this is the actual velocity we're setting, let me build and run and show what we're getting. We're actually getting a direction where the ball moves down off the screen. And let me see if this is working as a rotation. Let me plug in just some number like 2. And now we're moving a little differently. Let's move less. Let's put a very small value. Let's put in 0.2. So now we're moving just a little bit off. So we see we're starting to move in a circle where 0 is straight down, 0.2 starts to move a little bit counterclockwise, 2 moves a lot. If we give a value of 3,
almost up.
Almost straight up, and that's the key. Because if we did something like 3.14, it looks like we're going directly straight up. And that goes back to the idea of rotation in radians, where 2 pi would make a complete circle, or 1 pi would be 180 degrees, or half of pi would be 90 degrees. So that's where we can get exact directions out of this. So if I were to replace this with a constant math.pi, which I'll probably have to cast to a float, so now we're going straight up as opposed to straight down. And now the 90 degrees I was talking about, half of pi, we could do pi divided by 2, and now we're going into the right. And the direction to the right was one of the possible directions for a launch direction. As a matter of fact, given the logic I want to set up, I'll actually leave this as the default direction. We still have to account for random, but I'll start it off with just moving to the right.
Okay.
We'll say default to moving right. Or to the right. There we go.
Okay.
Now we need to take a look at a few other things. One, how do we get the random variance in place? And then how do we deal with moving to the left or moving left or right randomly? Let's take a look at the random variance and get that out of the way. The idea with random variance is that we see that the value pi divided by 2 goes directly to the right. To give some variation, we could take away from that value and then move down a little bit, or add to that value and move up a little bit. And that's where the idea for this range method came from as well. Let's make a method that will take in the minimum and maximum extents and then give some random between that. So let me put in an implementation so that I can add this on to the rotation. Going up to range, the idea here is to get a random value. So we're going to leverage that random object. and I'm going to return the value of random.nextDouble. Now, let me bring up the tooltip for a second. So we're going to be looking at a value between 0 and 1. So that's our starting point. We'll need to modify that so we get our min and max. But also, this is returning a double. And the method returns a float, so I'll need to cast that before I do the return. So we're returning casted the float, and we need to take this value 0 to 1, and we need to multiply it by the overall range, since we might have a range of greater than 1. What if we gave negative 10 to 10? That would be a range of 20. So, or 21 or whatever, close to 20. But the idea is I need to get this overall range. And that range can be viewed as the max minus the minimum. So that gives the overall possible range for these values. Now, onto that, I also need to offset by the minimum, because otherwise we're still starting at 0 because of next double. If we add on the minimum, then we start at the minimum, then go up to the maximum.
Exactly.
And that has range implemented, so now we can use range in conjunction with the rotational value. That is, after we've calculated a direction that moves us directly to the right, let's now add on to that some random variation using our range method. So let's give a range of, let's say, -1 to 1. And in doing that, we saw that since roughly pi, or 3, is a full 180 degrees, this should be about 60 degrees or so. So 1/3 of that, or 1/3 of 180 degrees. So about 60 degrees variation either way. So with that, now I should be able to run a few times and see somewhat of a variation. So there was almost horizontal, but we're moving down a little bit. And there's moving down a lot. And there's moving up a lot. So now we have a random variation, but the key here is that no matter which direction is picked, we have a constant speed. As a matter of fact, I could apply this now, since we're going to get a vector of 1, or excuse me, a vector with a length of 1, we could take that entire vector and multiply that by speed, and then we'll be given our desired speed. So that means we could do a final operation of this dot velocity times equals speed. So now given that the starting speed was 3, we now move at 3 going up, or maybe 3 going down, or maybe 3 going about horizontally. So that way we have a very accurate way of specifying direction. Now there's a few things left we need to add on. There's a few more things this needs to handle, and that is different launch directions. This is all great if the launch direction had been right, but now we need to handle the possibility for left or random. So let me start an if statement. Left is easy enough, just a matter of if direction is equal to launch direction dot left, then we know we need to go left. I'll worry about random in just a second. I want to get left working first, because we still have to consider how do we move to the other direction from right. So let's see, just jump down, and I'll block it in just because the if statement is going to get a little bit more in depth. So if we want to move to the left, how do we do that? Well, if we know that math.pi is 180 degrees, if we're moving to the right, imagine half of a circle, if we move to the other half of that circle, so if we move 180 degrees, we should be somewhere on that other side. So all we have to do is add another 180 degrees, or add pi. So what we can do is take our rotation, whatever rotation happens to be moving to the right, and add on to it the floating value. I think I need to cast the float here, because I'm going to use math.pi again. So math.pi, cast the float, and add that onto rotation. So wherever we happen to land on the right side, move 180 degrees and go from the left side instead. So that would handle direction.left. And before I get any farther, before I do random, I could prove that. I could jump back over to game. So right now we're handling game as, let me scroll down to, nope, too far, where we're launching the ball, we're launching it randomly. What if I change this to random.left? Do we in fact move to the left? And we do. And test a few times. So there's left, left about horizontal, left up some, so that's working. Or of course if we had set it to right, right being not equal to left means we always maintain our moving to the right. So the only thing left now is to handle random. So one last check we need to put in place. So reasons for going to the left. Well, if we're set to the left, or, well, let's not break that. Or another case, what if we have a direction of random? So, or, let me copy this entire thing. So, or direction is equal to direction dot random. Now, random doesn't always mean left. Random means there's a chance of going left. So this case needs to be a little bit more complicated. I'll encase the entire thing in parentheses, so I can say the direction is random and a random value of 50%, which could be as simple as maybe using that random object. So random.next. Let's give it next a value of 2, since that gives possible values or possible results of 0 or 1.
Mm-hmm.
So if that was equal to 0, it should have about a 50% chance of hitting 0. So now this means with this whole condition combined, if we were set to random, and random have, let's say 0 is right. So if we're looking for a random direction and then random tells us to go to the right, then set it.
Or to the left.
Or excuse me, left. I'm fine switching that. But now that should work.
Let's go ahead and jump back up the game and change that to random.
And let's specify a launch direction of random. And let's see what results we get.
So left. Left again. Left again. It's random, you'll see.
Still left.
Here it comes. I feel it. It's getting close. It's coming. Gotta have faith. Yay! To the right. To the right again. To the left again. And left again.
I almost wonder if that has anything to do with the amount of time the game has been running, because I mean we're not specifying a seed.
Mm-hmm.
I'll leave that for everyone else to research. If anyone wants to research and find out that the random happens to be happening so close to the game start that that's causing the offset, great.
Okay, so now we've got the ball launching.
And random directions in place. So yeah, that takes care of ball launch.
All right.
Now let's see what was next on the implementation.
Well, let's just go ahead and pull it back up, because now we're starting to get ahead of what my memory has. Ooh, that thing. I remember when we did that. Hang on one second. Let me grab a pen here. So we'll take this, come back in. So let's see. Jumping through here with focus. We've got displaying the pattern and paddles, centering the paddles, moving both with stick and keyboard. We've got the ball launching. So yeah, it makes sense. Next thing we're going to do is go ahead and get the wall collisions, the top and the bottom walls in place so that we can bounce.
All right.
Very cool.
All right, wall collisions. Let's jump back to Visual Studio. Still staying inside of the ball because we have this check wall collision method. Let's implement that. And then a preview of why it's inside a ball. We have this override to move. And since wall collision is going to be used in conjunction with move, it's move that actually brings us to the wall in the first place. I'm going to use move to not only move the ball, but to perform that check. As a matter of fact, instead of just explaining, we're going to say that we're going to move, which is a call to base.move, and then we're going to make a call to check wall collision.
So basically, after we've moved, we're going to check to see if we've collided with the wall.
Did I actually call that wall? Because it's looking like check collision exists.
No, check wall collision.
This dot check. There we go.
Yeah.
So we move and then check wall collision. That means it's going to be up to a wall collision in order to move it back on screen if it happened to get a little bit off screen. But alright, everything now is depending on wall collision. So let's see, we need a series of checks. We need to see if maybe we've gone off the screen and Y above the screen, or maybe we've gone off the screen below.
And this is, again, something you guys have seen several times in the past.
So yeah, same style of bounce code.
Mm-hmm.
But the value we're looking for is this.position.Y. And let's check the top of the screen first, which means if Y has gone less than 0. If it has, we have collided with the top of the screen. And in that case, since we may have gone off the screen a few pixels, let's reset the position to exactly 0. So this.position.y equals 0. Let me set that to F, just because we're dealing with floating point calculations. And now after we've bounced, we also need to remember to reverse the velocity in Y. So this.velocity.y times equals -1. And that should handle bouncing off the top of the screen. So if that wasn't the case, maybe we've hit the bottom of the screen. So let's check if this.position.y has gone beyond the actors. So actor.screenBounds.y. Now we want to wait for the, we want to check the bottom, not the top of it. So we actually need to say y minus its own height. That is this.texture.height. So if we have gone past the screen bounds minus the texture's height, then the bottom of the actor has collided with the bottom of the screen. So in that case, we need to reset the position Set the position y equal to that value. That is the screen bounds y minus the height. So this position at y, screen bounds minus height. And we again need to reverse the velocity, which I can, if I wanted to, simply steal from here.
Okay.
And that should be taken care of check wall collision. Now let me run and hope that I get a random value. I might even reset that vector. Matter of fact, I'm just right off the bat going to reset that.
Just so you aim it more at a wall?
Yeah, what I'm talking about is here in launch. Let me duplicate this line since we have a random range that's giving us our final direction. Let me comment that momentarily and add on a specific value. Like, let's add on 1F. This will make us move up, hit the top of the screen, and then bounce down. We could add even more if we wanted to. We could add maybe 1.7. So we get a value high enough. Actually, we've gone all the way back past, and we're moving in the other direction, but that's fine. Or maybe the random hit, I don't know.
So there we go. We're able to test, though. Top and bottom is working
so
just
yes,
right.
Both top and bottom look correct. So I can take out our test line and then put the random back in.
Beautiful.
So that takes care of wall collisions for the ball, because the only thing left for the ball to collide with is the paddles.
Okay. So let's start on paddle collision.
All right, paddle collision. Let's see.
So this is where we're going to have to deal with the actual check collision.
All right, this is that check collision that's back in Actor. Actor has the static, or is that at the bottom? Check collision.
Mm-hmm.
The idea here is that we take two actors, look at them as rectangles, and then see if those rectangles intersect.
And at this point, feel free to go ahead and break out a piece of paper and trace through what we're doing. It's very easy as long as you draw it on a piece of paper. Otherwise, it might be just a little confusing to see. We're going to get into a closer look at collision detection and even breaking down simple collision detection like this rectangular collision check here. Coming up in the upcoming volumes with some of the games we're going to be doing.
Right.
But like I said, this is very simple. If you draw it out on a piece of paper and you draw your left-hand corner, right-hand corner, and you assign numbers and widths to everything, you can figure this out, and heights. You can figure this out real quick.
Right. The idea here is that there's a formula for checking two rectangles and to perform the check in as few actual checks as possible. Because, I mean, you could go about it many different ways. I mean, if you looked at all the points on the rectangles as points and checked to see if those points were in the rectangles, you could check 4 points against one rectangle and another 4 points against another rectangle, and that would be a result.
Mm-hmm.
But that would also be a lot of checks. Mm-hmm. There's a formula where you can check as few things as possible. I'm going to write the formula down, and then I'm going to write variables to satisfy that formula. So what we're actually going to do is return the result of 4 checks. So we'll return 1 check and then 3 others. So the first check is going to be return x1 is less than x2 plus width 2. And y1 plus...
y1 is less than.
Skipping past. y1 is less than y2 plus height 2. And jump down a line. And x1 plus width 1 is greater than x2. And y1 plus height 1 is greater than y2. So those are all the checks. That's the formula for doing 2 rectangle intersection in 4 checks.
So now the question is, what is x1, x2, width 1, width 2, height 1, height 2?
Well, x1 is going to be the actor's position x.
Mm-hmm. For actor
x2,
A.
or for actor A. x2 is going to be actor B's position x.
So let's go ahead and fill in all these variables.
Okay. Position is held on the actors as floats, so I'm going to define the variables as floats. So we'll have a float called x1, and that float x1 will be equal to actor A dot position dot x. So I can copy this a few times now because we're actually going to have 4 values: x1, x2, y1, and y2. So y1, x2, and y2. Now those values come from, starting with y1, comes from actor A dot position y. x2 comes from actor B, comes from actor B's position x. And finally y2 comes from actor B's position y. Alright, let me jump up a line. Now, 4 more values. We have width 1, width 2, height 1, and height 2.
Okay.
Those come from the texture height of the actors. So we have, I'm going to store these in integers just because the texture dimensions are in integer. So the first one is going to be width 1 and that is going to be equal to actor A dot texture dot width. And then 3 more, where we have width 1, height 1, width 2, and height 2. Now, height 1 is equal to actor A's height. Width 2 is equal to actor B's width. And finally, height 2 is equal to actor B's height. So there, that fills out all 8 variables necessary for this formula. And now if we build, everything builds, so everything is happy for satisfying these values.
Very, very nice. So now what we need to do is...
Well, in order to use these, we need to go back to the game and put in those checks, because now we have something that we can use to check. But we need to be at a point in code where both the ball instance and the player's instance are in scope, and that is back in the game where both of them exist as fields. So that means we'll go back to the game, back down to update, and now we can perform checks to see if ball-paddle collisions have occurred. So the first of those is going to be a check of actor dot check collision between which 2 actors. Well, actor A will be the ball, and actor B will be player 1. So we'll see if the ball is collided with player 1. And if that's the case, we want a few things to occur. First, we want the ball to start moving in the other direction. Take the ball's X and reverse it. Now this is a little trickier though, because I don't want to just reverse it. I want to make sure it goes, if we hit player 1, make the ball move to the right. Absolutely to the right, and have no chance of the ball sitting there and jittering back and forth. So the way I'll do this is to set the ball's velocity in X equal to, well, not plus, but equal to the absolute value of its X. That means if it was, that way we'll always come up with a positive result. It will always move to the right. That means we can take in math.absolute for ball.velocity.x. If it happened to, for some reason, already be moving in X, if we had already reversed it, we still continue to move in the positive direction. If we're moving in the negative direction, to the left, then we'll change to the positive direction. And one other thing we want to do at this point is to apply the spin percent. Since if we have just detected a collision with the ball and the paddle happens to be moving, it needs to impart some motion onto the ball. So let's impart that with ball.velocity plus equals the player speed. Remember now, at this point, in order to impart paddle velocity, we need to know what the player's or the paddle's current speed is. And that is held in player 1 velocity and player 2 velocity. Since we're checking player 1, we're going to use player 1 velocity. So we could impart player 1 velocity, though if we did this, we would impart the entire velocity and add that on. So we'd add the 5 velocity in Y, possibly, off of a paddle to the ball. And instead we want to have a percentage. As a matter of fact, we have a percentage defined by the spin percent constant. So we'll plug in times spin percent, which right now should be set to 0.5, so we only catch half of the velocity off of the paddle. And I believe that should be it. Let me build, and let me go ahead and duplicate this. Since the starting direction is random, let me put in the collision check for player 2. So I'll simply copy the entire if block, replace player 1 with player 2, and then the velocity imparting will be imparted from player 2's velocity. And everything else should be the same. So we can build, and, well, we can run and see if we have working collisions. Oh, there's a collision off of player 1. And player 2, not so much.
Player 2 go boom.
So what are we missing for player 2? Well, it looks like we have the velocity is alright. Now look what I'm doing for the direction. I'm saying continue to move X in a positive direction. That's wrong. That is off the screen if we're moving off the right of the screen.
We need to minus that.
So I want the opposite. That means get the absolute, but make sure that we always move in the negative direction. So let's try this again. So alright, so player 2. There we go.
See if I can put a little spin on it.
Oh, yeah. Yes, you've imparted more velocity by moving the paddle, and even more.
It's getting dangerous. See, we're going to have to put a... Oh!
Almost.
And of course, there's nothing to relaunch it, and paddles go off the screen.
Woo. Noticed another problem, and that is there is no checking, so the paddles are never kept in balance. They can go right off the screen.
Hello. Hello. Hello.
But we have verified that these two checks are now working.
Yep.
Collisions for player 1 and collisions for player 2. So let's take just a moment and focus on the player, make sure that the player paddles are locked to the screen.
Okay.
And to do that, I'm going to jump back to the player class and jump back to the reason that we're overriding move. Since we're moving, and in Actor we know what the screen bounds are, after a move we can check and make sure that we're still on the screen. So let me do just such a check. Let's start an if statement for the position, more specifically the position in Y. So let's say if this position at Y, let's check maybe the top of the screen. Let's see if it has gone less than 0. If it has, then we need to relocate back onto the screen. So this .position.y would be equal to 0.
Simple enough.
Otherwise, maybe we have gone off of the screen, off the bottom of the screen. Or that would be this .position.y has become greater than the actor.screenBounds.y. Well, we want to check the bottom of the paddle, not the top. So we need to offset for the paddle's height, or this texture.height. So if the bottom of the paddle has gone off screen, move the paddle so the bottom is back on screen, or this position.y equal to this value that we checked against.
All right, let's see if it works.
So let's run.
And up. Hey, I can't go any higher. Ah.
And down, and
I can't go any lower.
Can't go any higher above, so locked.
And
locked.
Oh, man. And try keyboard. Let's make sure keyboard, same thing. And up, and there we go.
So yes, the keyboard is locked because
of course,
the move
same
is independent
thing.
of keyboard and mouse.
That's
we have that
right.
all wrapped into the same input method.
So everything's looking great, except we need score, and we need it to relaunch the ball now after it goes past a paddle.
And that's the key. We need to detect when it has gone past the paddle. And I'm defining that as the moment it goes completely off screen.
Right.
So that means some more checks. And now where to put these checks? Because, I mean, we have options. We know where the ball is and we know the screen bounds. But instead of doing this check inside of ball, I actually want to do it inside of the game's update. And the reason for that is the ball going off screen affects the player. The player holds the score. So when we do that check, we need to have access to the player, and therefore we need to be inside of game in order to see that. So jumping below the ball and paddle collision checks, let's do some checks to see if the ball has fallen off to the left or right of the screen. Let's start with if the ball has gone off to the left. So that would be if ball.position.x is less than... Now I want to make sure that the ball moves completely off screen. So that doesn't mean the left side. I want the right side to move off screen. The right side would mean I'd have to move off entirely in the negative for however wide the ball is.
That's right.
Or negative ball.texture.width. So if we're completely off screen to the left, then we have fallen off screen. That means player 1 has lost the ball and player 2 gets a point. And also the ball now needs to relaunch now that it's off screen. So we can take the ball and tell it to launch. I might change the order of this in a second because I like the way it sounded with the score happening first. It doesn't really matter because they both happen at the same
we know
time.
which way it needs to launch though because it just went off the left side of the screen, so we need to launch it to the right side.
So we're going to specify a launch direction, and that is launch direction.right. And the speed is going to be the starting speed for a ball. So we dump any speed that the ball might have, and we relaunch at the start speed. And then we take the score. Now we need to take player 2's score. And we need to increment that. So player 2.score should be incremented by 1 because player 2 just got a point.
Mm-hmm.
And that is the check. So I should be able to copy this check now, paste the duplicate, and then change this for falling off the right side of the screen. So the right side of the screen is if the left side of the ball has fallen off screen, or the position X is greater than the screen width. And if that is indeed the case, we need to relaunch, but this time relaunch to the left. And if it has gone off that side of the screen, player 1 gets a point. And I think that's it.
And we can test it. We won't see scores yet, but we can test just to make sure that the ball does indeed.
So missing the ball, click, and now it launches towards your side of the screen.
And tink, it launches
then back
towards
to
your
mine,
side.
Then back to yours.
And smack.
And once again, to the left again because it's launching
smack.
towards yours.
Yeah, I'm just not helping in testing that out.
And again to the left.
Okay, I'll let it test. And to you.
To the right.
So
now we need to be able to see some scores because we are incrementing score. Score exists.
Mm-hmm.
We just aren't drawing it yet. So let's take a look at that. Let's jump back down to draw and get the HUD working, the scores displaying. So we'll jump in after we draw the ball. And let's make our first call to draw string from the sprite batch.
We can set the left side up real easy.
So we're drawing string. What are we drawing? Well, we have that font stored in font, and we're going to draw the text. It's simply going to be the score dot to string. Let's draw player 1 score on the left, and we'll have player 1 dot score dot to string. The position, we know how much it is, or it's supposed to be offset, so we can plug that into a new vector 2, where we can plug in the text padding for X, and again the text padding for Y. And finally we'll draw with the foreground color. Alright, we run, and now the number 0, and if I let the ball fall off the screen, clicks over to 1. We can't see my score yet, but if I let the ball fall off again, clicks over to 2.
Perfect.
So
and
now,
as you were saying earlier, there's the reason why it's been placed where it's not in the way of the paddle.
Exactly.
Okay, cool. Now, getting your score in is a little bit trickier because, like we had said earlier in the requirements phase of this challenge, we did not want it to, basically we wanted the score to be right aligned. We didn't want it to start going off the screen.
When we have the score placed over here on the right, we don't want to worry about it, maybe a 2 or 3 digit score getting off screen. And that means we need to handle right aligned text. So to begin with, I'm just going to copy and duplicate the line. I almost should have done this in the beginning, but we didn't have the right side of the screen. If I draw this here, we still have the same place. We do need to get the right side of the screen for the positioning, and that would be screen width. If we draw this immediately, though, then that's the very left of the text. So the text is actually
all
off screen.
Yeah.
So we need to get some value that will bring it back on to the left. So that means I need to come up with some value.
Well, even right now, if before you do that other value, if you just subtracted off that text padding.
So minus text padding.
That'll bring it back over onto the screen, but it's, well, you can show them. It's not going to work really well. First of all, it's not aligned properly.
Because we're eating up some of our padding value by drawing a 1 over it, instead of being outside of the padding value.
And as soon as we go to 2-digit numbers, it's going to start drawing off screen.
Right. So we need to come up with some value. Basically what we need to account for is the fact that we need to take into account the width of the text, and then shift back to the left based on that width. And so what I'm going to do is I'm going to make a variable called right align offset, and we'll set that to the width of the text, and then we could subtract off right align offset, and then that'll position us properly for aligning to the right. So let's make a float variable and call it right align offset, and then set that to our width. The width of the text in question can be derived from the font's measure string method. So measure string will take in the text that we need, and this is going to be player 2's score, player 2's score dot to string, and sure, I could store a string variable, but I mean, since we're not doing anything else here, I'll just plug it in directly. Now after this, measure string is going to return a vector 2, and I'm only worried about x. We don't need to worry about height in this case because the text doesn't go up and down in the character set we have. So let's take the x only, store that in right align offset. Then when we're subtracting things, we can subtract the padding and then subtract the right align offset. And when we do that now, we can see that right off the bat the text is aligned properly. And then as the score goes up, let me actually change the score so that it increments faster. I'm going to set the player 2 score to be incremented by 87 for every point. So immediately we'll get 2 digits as soon as I get a point. So there's 87.
Well, I don't want the ball to go by.
And you can actually see the score, you can see drawing out to the left more. So every time it increments, we see it moving to the left, or rather following the behavior of right aligned text. And in the end of the day, what that gives us is it properly respects our text padding on both sides.
And to be honest with you, that's everything, isn't it?
Aside from the fact that I've immediately gotten 435 points.
And it's going to take me forever to catch up.
We should probably set that back to 1. But yes, really, that takes us through score, and I believe...
too slow. Dun, 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 dun.
Most exciting game of Pong ever.
Woo.
Let me see if I can counter that speed and take it back off. No, too late. There we go, I took some of the speed back off. So the speed can be imparted or reduced if you move the paddle in the opposite direction.
Mm-hmm.
So, I mean, that's working nicely for a good strategy element.
Boom. So there you guys go. Knowledge Review 8. A Pong-like game. Woo! Yeah, there's some challenge. Da-da-da. Speed! Well, that wasn't much speed to that.
And unspeed.
And more unspeed. Alright, very cool. So, we're going to stop right here while I'm winning. And let's go ahead and jump back over to the whiteboard real quick and just make sure we've got everything. So, of course, we got the wall collisions in place. We've got the paddle collisions in place. And we have got the score and relaunching the ball in place. Now, of course, if you were paying very close attention to this, there is kind of a small bug in there, wouldn't you say, Logan? We're not taking into account the top or the bottom of the paddle at the moment. So you've got a paddle. We'll make a really big one at the moment. What happens if we manage to get down here and then move our paddle down like this? So that's just something to keep in mind. It's not 100% perfect with what we've got at the moment. The idea of this knowledge review is just to get a very simple game setup, just like we've shown you here. Now, as we progress into the later volumes, we're going to become sticklers on the collision detection, and then we're going to have to start accounting for stuff like this.
Right, but in this case, that was one reason to use the absolute velocity assignment, is because if you moved, because what you're showing there is what would happen if you moved the paddle so that the paddle or the ball was suddenly inside the paddle. You might have a case where if you reversed every time you collided, you would have the ball stuck to the paddle now simply vibrating back and forth. But since we're setting an absolute velocity...
Yeah, it'll still detect that there's been a collision and poop, out we go.
Right, even if there's multiple collisions at the same time, it'll still continue to move out of the paddle and eventually be free and continue on its way.
Exactly, but just in case you happen to see your paddle slide down over it for just a fraction of a second like that, just keep in mind that's what's going on, and we're not pushing you guys on hardcore collision detection yet. That's coming real soon. So, anything else you want to add to this, Logan?
Nothing comes to mind. I mean, we've gotten a result that's identical to the one we demoed.
So once again, ladies and gentlemen, this was the knowledge review answer, one of probably hundreds of different ways that you can do it. And you may have done it in a similar method. You may have done it completely different, but as long as you fulfilled all the requirements that we set out in the last video, excellent job. And if not, I would highly recommend going back and studying everything that we have presented throughout Volume 2, because this stuff is going to become very important, because in the next video we are going to begin Precision, and Precision is going to be the most complex game that we have written to date in the XNA Extreme 101 class. So with that wraps up this section on the introduction to the XNA framework. Thanks a lot.